Hello guys, this is Miscellaneous Exercises and Consolidation, and there's a very important area covered in this exercise called integration by recognition. So I want you to concentrate really hard and make sure you understand. Alright, here we go. Integration by recognition. There are two steps in these questions. Integration by recognition. The first step is you are asked to differentiate a given function, and then in step 2 they ask you to use the results of the differentiation in step 1 to integrate part of the step 1 derivative expression. Now that all sounds like a bit of a mouthful, so I think we'll just get into an example and show you how it works. For some reason students find this incredibly difficult, but it's a really simple cookbook procedure if you can just grasp what's going on. I'll try to make it really simple for you to understand. Example 1, we've got f of x equals x log x, and in part 1 we have to show that the derivative of this is equal to 1 plus log x. And then in part B we're asked hence to evaluate the integral of log of x base e with respect to x. Now I'll show you how easy this is, so just come right along with me and relax and we'll have a good time, and you will understand hopefully by the time I get to the end. Alright, part A, that's just a product rule, so not anything difficult there. Y is x log x, so remember left d right plus right d left, where d means derivative of. So we've got here dy dx is the left term, which was the x times the derivative of the right, which is 1 over x, plus the right, which is log x times the derivative of the left, which is the derivative of x, which is 1. So that's looking good. Simplifying that, clean up line, we get dy dx is just 1 plus the log of x. Now, I want you to notice very carefully what the answer to this is and how it relates to what you're being asked in part B. Do you see this log x here? They're asking you, hence, to evaluate the integral of log x with respect to x. And this is something we can't do analytically because we haven't been taught how to. So we're using this integration by recognition process to get around this and find a way of doing it through this scaffolded kind of question. Now, the first thing I want you to do, ladies and gentlemen, is to recognise what's here compared to what's here. And I want you to get this in part B on the left-hand side of the equation all by itself, okay? So have a look. That's it. That's what I want you to do. That's the first thing you do. Reorganise it so this is the left-hand side all by itself. Once we've done that, we just integrate both sides with respect to x, and we then work on the right-hand side as our answer. That's what we do. It's really simple, so just watch. So therefore, if I integrate both sides with respect to x, I can say that the antidiff of the left-hand side equals the antidiff of the right-hand side, yeah? Alright, so that means that this is equal to this. Now, I'm not going to try and do anything with that. That's what I'm trying to find from up here. I'm going to work on the right-hand side, okay? And the right-hand side is going to give me the answer to what this is, okay? Which is what I'm being asked for. Now, you'll notice that at the very beginning I always start with let y equal whatever the thing is. I don't work with f of x's for the sake of these calculations because it's nice to have a single symbol, and you'll understand why in a moment. So that's always my starting line. Now, let's go down here and work on the right-hand side. We've got to work out what the integral of dy dx minus 1 is with respect to x, ladies and gentlemen. Now, I've split this up into two separate bits. So that's integral of dy dx with respect to x minus the integral of 1 with respect to x. Do you see that? Now, I want you to get your thinking cap on and tell me what is the antiderivative of dy dx. What do you think? Well, let me put it this way. What is the derivative of y? Well, it's dy dx. So therefore, what's the antiderivative of dy dx? Well, it's y, isn't it? Of course it is. So therefore, we get that. Okay, don't forget the plus c, by the way. Now, you might be looking at that and thinking, good grief, well, so what? What do I do with that? Well, ladies and gentlemen, what you do with that is you go back to my opening line. That's what y is. So you just use that, put that down here, and see how easy it becomes to work through. There it is. So you just get this is my y minus my x plus c. So therefore, there's my answer. There is the left-hand side of what I started with over here, and there's the right-hand side worked through to completion with a beautiful result. Okay? Alrighty, here's another example for us. Same procedure. Two-step process. First step, show that the derivative, or find the derivative, or some such wording of this here. And in the second step, hence evaluate this antiderivative, which this thing here, this 1 over sine squared 2x, is going to come out of the derivative of here. See, it's here. See? Except it's got a 2 on the top, but we can sort that out. No problem. So let's go for it. Part A. Let y, there's my first step, that's my opening gambit. Let y equal that thing there. Now I'm going to use the quotient rule now to derive that. Okay, so remember, bottom d top minus top d bottom over bottom squared, where d means derivative of. So bottom is sine 2x, derivative of the minus cos 2x term is plus 2 sine 2x, minus top d bottom, there's top, and then d bottom is 2 cos 2x over bottom squared. That's right, isn't it? Now, what's that besides a very big mess? Let's just flesh that out a little bit. I've taken out the common factor of 2, and it looks like, oh, look at that, sine squared 2x plus cos squared 2x, which of course you know equals 1. Well done, good on you. So therefore we just get 2 over sine squared 2x, which is what we had to prove, and there's our QED. Beautiful. So that's part A done. We've done the derivative, and we're going to use that derivative to do part B in the manner which I showed you in the last example. So, okay, we start with this. Okay, dy dx is that. Therefore, I'm getting what they want on the left-hand side. Okay, this thing here, just swapped sides here. That's all I did, and I'm divided by 2. So, therefore, this thing, getting ready for this step, this thing would be a half of dy dx, wouldn't it? Now I'm going to leave that alone now. I'm going to anti-diff both sides, and we're required to do a definite integral, but that's no problem, just an extra step in the procedure. The worst of it is already done, guys, because we're just going to anti-diff this, anti-diff that, and you see what happens. It just gives up without a fight, and it's pretty marvellous. So we know that the anti-diff of this must be the anti-diff of that. Okay, now what's y? Y is here. See? How marvellous. So we're going to substitute for y on the right-hand side, and we're going to work on the right-hand side. Okay? There it goes. Looks good, doesn't it? Yes? Okay, now all we have to do now is evaluate that definite integral thingy there, and we're done. We're done. So I just had to go over the page, recapping where we got to. There it is. Let's have a look and see if it looks right. Yes, it does look right. Yes, it does look right. It does look right. Okay. Now this term here, guess what that is? It's a 0 because cos of pi and 2 is 0, isn't it? This one won't be 0, but it'll be very simple because cos of pi and 4 equals sine pi and 4, so it's just going to be a half. I think the answer's a half. Ah, it is. That's marvellous. So that was easy, wasn't it? When you think about how easy these things are, please don't get all mixed up. They're really quite simple. Example 3, another one, exactly the same thing. Okay, so we're getting used to them now. Let's do the derivative of f of x, but I'm going to call it y, okay? Because I don't want to be dealing with f, I just want to be able to substitute back for what y is when I get through the antiderivative process, yeah? Let's do the derivative. That's going to be a product rule, so it's 2 times left d right plus 2 times right d left, or just putting a 2 in front of each term. Yeah, makes sense. Yes, it does. And therefore we get that. Okay? Good. Now, we're going to use that result to do the part B hence bit. Okay? Now, you can see already, see, here's the bit that they want us to anti-diff. So we're going to isolate that on the left-hand side of the equation, get rid of the minus 2 bit, and then Bob's our uncle again, you see. There we go, that's part B. Now let's divide both sides by negative 2, and we'll get x sine x is minus a half dy dx plus 1 cos x. Alright, now we're ready to go now. We're going to hit it with a knockout punch with the antiderivative. It's a definite integral, no problem. There it is, yeah? Now, of course, ladies and gentlemen, you know what this beastie is, don't you, by now? He's up there waiting for us to put him in, to substitute him into the equation, you see? So let's do that. There it is. So all we've got to do now is go through the process of evaluating these things here, and we're done. We're done, guys. So it looks like minus x cos x, I'm putting them in the same bracket here, okay, just to avoid it looking so ugly, plus sine of x, evaluated from pi on 4 to pi on 2. This is going to be a snap, guys. So it's going to be minus pi on 2 cos pi on 2 plus sine pi on 2, the first term of which is going to be 0. Of course it is. And then it's going to be plus pi on 4 cos pi on 4 minus sine pi on 4. That's right, isn't it? Yes, yes. So once you do all that, it's easy. There's our answer. We're just cleaning it up a bit. And there it is. It's easy. You see, don't get confused, guys. Now, lastly for this lesson, when we simply can't find an analytical solution to an integral expression, CAS is our choice of weapon to find either an exact solution or, in many cases, a decimal approximation. Sometimes CAS just can't wade through all the algebraic mud and stuff, integration horrors, and therefore it just gives us a decimal approximation. But sometimes it does give us an exact answer, and I've chosen 2 examples where it actually does. Okay, so you have to realise that a lot of integration can't be done analytically, or is certainly beyond the scope of our course, and you've got to be able to make the value judgment when you get to the exam what to do. You know, can I do this, can't I do this, you know, what's the simplest way, what's the quickest way, and all of that comes with practice, yeah? So here's our example. Those 2 things, I've just basically went straight for the CAS, because there's no way we can do that analytically, and there's certainly no way we can do this analytically. So here it comes. There's the first one, and the CAS came up with this amazing exact answer. Good heavens. And here comes the second one. There it is, and also it came up with an exact answer for us, okay? So please practice this integration by recognition. It's very, very important, and you need to know how to do it. All right, see you soon.